In the meantime, you need to know what an atomic mass unit is. Now, I mentioned earlier that these masses in grams are unbelievably tiny. They're not practical to use. So instead, researchers, scientists, chemists, whatever, have come up with this kind of new idea here. They just said, you know what, let's make up a unit. So they said, instead of measuring it in grams and having this ridiculously tiny number, let's just say that protons and neutrons, since they're pretty much equal, let's call them each 1 AMU. Let's call it 1 atomic mass unit. Let's make up our own unit. So they call them 1 AMUs. And electrons are unbelievably small. We're going to say that they don't even count. We'll say that they're equal to 0 AMUs. Okay? So chemists decided to use a value that they created, this AMU stuff, and it's a value that's based on the isotope of carbon-12. Now, you don't necessarily need to know what isotopes are at this point. You might have heard the word, but you don't need to know that. You just need to know that carbon, a specific type of carbon atom, has 12 things inside the nucleus. 6 of them are protons, 6 of them are neutrons. It works out perfect, 6 and 6. So they decided, let's set this equal to 12, and then let's set up a unit, AMU, and each one of these things are 6. Or I'm sorry, each one of these things are 1, so it adds up to be a total of 6 AMUs there, and on this side we got 6 AMUs here, and it's equal to 12. So now they can compare everything according to carbon. It's kind of like me saying, I'm going to take the tallest kid in the room and then measure everybody according to that kid. So let's say Johnny has a mass of 6 feet, and Sally has a mass of 3 feet. I'm going to say that Sally is 0.5 Johnny's. Or let's say that somebody else is 3/4 of Johnny. I could put somebody else's 0.75 Johnny's. So we're comparing everything to a basic value here, and they just kind of sort of arbitrarily picked this. There's a little more to it, but for now, all you guys need to know is that they picked the unit and they set everything else equal to it. So if we're talking about one atom, if we're talking about just one atom, we're not going to use grams because I said that was unbelievably small. So if we're dealing with one atom, we're going to deal with AMUs. Okay? So you look at the average mass of one hydrogen atom, it's AMUs. If you look at the atomic mass of chlorine, it's in AMUs. So if you look on the periodic table at that number that's not rounded there, that's the atomic mass, and that's measured in AMUs. If you're dealing with just one chlorine or one hydrogen or one whatever atom, one atom equals AMUs. Now, that's not practical, so people have decided to use the mole. They put this ridiculously big group of atoms together, and then they said, well, if you have a mole of this stuff, it's equal to that many grams. So every time you refer to those masses on the periodic table in grams, you're really referring to 1 mole of those atoms stuck together, and that'll be equal to that mass in grams. Okay. So one atom, AMUs, many atoms, a mole of atoms, we call them grams. Now electrons, take a look at the mass here, even smaller. I think the other mass was times 10 to the negative 24th for the protons and the neutrons. This is times 10 to the 28th, so it's even smaller, makes a huge difference. Remember, every time you add another 0, it's 10 times smaller. So this got much smaller than just the even times 10 to the negative 24th. So we're going to ignore the mass of electrons. Ignore the mass of electrons. When you deal with the mass of an atom, you're dealing with protons and neutrons inside the atom. You're going to ignore the mass of the electrons. But we do have to consider their charge. Electrons are negative. I hope you know this by now. Protons are positive. And when you take a bunch of positives and you take a bunch of negatives and the numbers are equal, then they cancel each other out and we end up with something that's neutral. So if you have 6 protons and 6 electrons, let's do it this way. 6 electrons, 6 negative charges, 6 positive charges. The 6 and 6 cancel each other out, and you end up with a neutral charge. And you can imagine if you had, let's say, 5 electrons and 6 protons. Well, you have an imbalance here. You have 1 more proton, so it would be a positive 1 charge, 1 more proton. Or what if you had 5 of these guys and only 4 protons? Now you have 1 more electron, and that would give you a negative 1 charge because you have 1 more electron in this situation. So we're going to right now assume that everything is neutral. Later on, we're going to learn what happens when the electrons come and go. What happens if you get more electrons, what happens if you lose electrons, and then we'll have what we call an ion. And that's got a charge, and you probably know that word already. But for now, atoms are neutral. We're going to talk about this word happy. I'm going to put it in quotes here because it's not really a chemistry term. But we're going to say that they're happy when they have a certain number of electrons. That number doesn't always have to equal protons. So you might have sodium, for instance. Here's sodium with 11. Where's my pen? All right. 11 protons and 11, oops, that's not an H, 11 electrons. This is sodium. Sodium is not happy that way. Sodium actually wants to end up with just 10 electrons, so it's going to have to lose an electron along the way. Once it does, it's very happy with that lost electron, but that makes it a positive 1 charge. And then it's happy, it's stable, and so forth. We'll talk about these ions. This would be an ion because it has a charge. We'll talk about these ions later on, but right now we're just going to deal with neutral atoms. What happens when positive protons are equal to negative electrons. And there you go. So on the left we got hydrogen, 1 proton, 1 electron, it's neutral. Not happy that way though. Carbon, 6 protons, 6 electrons, not happy that way, wants to get more electrons, wants to share some. Here's gold, 79 protons, 79 electrons. Right now they're all neutral, not necessarily happy or stable. Now, just a quick little aside here to put this in perspective. If we dealt with an atom and we could blow up the atom to be the size of a huge football field, gigantic football field, oops, the nucleus would be a little tiny, tiny, tiny marble down there. Little tiny marble on the 50-yard line. The rest of this space here would be the electron cloud. The rest of the space would be seats open for people to sit in or places for electrons to zip around in. But the nucleus would be this little itty-bitty tiny spot down here on the 50-yard line. So there's a huge difference between the size of the entire atom and the size of the nucleus. Nucleus is unbelievably tiny compared to the rest of the atom. But if you think about it, let's say this stadium was empty and there were only 10 people looking for seats. Well, those 10 people have a lot of seats to sit in. They could sit anywhere in these in this entire stadium, but at any one point they're only going to take up a max of 10 seats. So there's a lot of empty space, and that's the same thing with the atom itself. Lots of empty space, places for the electrons where they could be, but they may not always be in all of those spaces at once. So lots of empty space. All right, let's get down to the nitty-gritty. We can represent the atomic and the mass numbers with what we call a nuclear symbol. Kids get confused because we're going to show you this symbol and we're going to tell you also the isotope name. This is called a nuclear symbol, and we write it like this. We put the symbol over here on the right, and then we put the top number is going to be your big number. That's going to be your mass number on top, and the atomic number will be on the bottom. I can't spell today. Atomic. Alright, so mass number on top, atomic number on the bottom. The superscript is your top number, so this is the total protons plus neutrons. This is the total on top, and this little bottom number here is your subscript written down low, and this is just your protons, just your atomic number. So you can imagine that if you know the protons and neutrons up here, and you know the protons down there, you could easily do some subtraction, because the protons will cancel out. You do some subtraction to figure out how many neutrons are left in that particular atom. So this nuclear symbol is a nice quick way to give us lots of information. For instance, we've got down here the carbon-12. We've got 12 up top. That means 12 things inside the nucleus, protons and neutrons. And down here, the 6 tells us that 6 of them are protons. So they're going to cancel out. 12 minus the 6 is going to be 6. And we know that there's 6 protons and 6 neutrons.